So, hello everybody. It's nice to see you all today for the start of this course. Um, I was there last year, but I came very late, so I didn't see the thing from the beginning. And I do hope that the program, you like the program and what we have put up for you, particularly the other member of the committee, and Alain is here, but there was other people like Victor Geza from HBP, Mira Kalish from SP8, then there was a lot of people that was involved in the making of the program. And through the several discussions that we had, we tried to see what was unique about the Human Brain project, and and I hope this program this week will represent what is unique about the Human Brain project. It's about what Alois was talking about, this multi-scale representation of the human brain, the both human side and animal side, for understanding the brain. And understanding disease is one of these main goals. And this goal can only be achieved through integration of data, integration of model, and also the way that we can bridge this gap between the different scale. So the program is organized that you will have a choice. You will learn about different diseases from stroke, epilepsy, and dementia. You will learn about how you can investigate these different diseases using different type of data from neuron to neuroimaging data. And it's pretty exciting program that I hope you will like. During this week, you will have like a lecture on these different diseases and type of data. And you will have also the opportunity to have your hands-on session and to do some projects. And the projects will be throughout the week. You will be deciding which topic you want to do. But at the end, I think in Friday, the idea that we can share together how really we can bridge this gap between the different scale of representation. One of this challenge. If we solve it this week, I think we'll deserve Nobel Prize, but I don't think we'll solve it this week at all. So the topic, as I say, is influencing clinical diagnosis from treatment through the use of data mining and possibly modeling. That's the key, I think. The modeling approach is really the key if we want to bridge this scale. And I will be talking during a little bit about the medical informatics platform, because that's the one of the platform which is about disease in the Human Brain project, but it's not the only part of the Human Brain project which is about diseases. And I put together this idea that together we have to develop a better understanding, because we need neuroscience, we need fundamental neuroscience, you need clinics, you need all this sort of discipline to understand the brain diseases. So for my part, I come from Switzerland, from Lausanne. We have a small team in the Department of Clinical Neuroscience. We have an MRI. We do see a lot of patients, mainly dementia, but also Parkinson's disease and epilepsy. And we were involved through the Human Brain Project because of our expertise mainly in neuroimaging. So we are mostly on the whole system neuroscience. But the Human Brain Project is more about going through the different scale, as I said, from neuron to the highest level. And it's true that we don't know much about the human brain, but we know a little bit at different scale. And science have really evolved, and we have a bit of understanding and modeling. And I always take the example, because I'm located a bit on the top, about psychology and neuropsychology, which is like 100 years of old or even more. Through these experiments and very simple experiments through dissociation, we know about the fractioning of memory, for example. And but now through all these techniques of gathering data at different scale, we know a lot about memory at this different scale, how they happen at the level of neuron, how they happen of the synapses, etc. But what we don't know is what gives rise to this phenomenon that we call memory in the brain. And this is very particularly important because, as you know, memory is one of the hallmark of brain diseases. It's something that's dropped very dramatically when you reach the age of 40. Is really visible. That's is one of the first brain function that go really down, and it goes very down in many diseases. And this is why it's important that we deepen our understanding of neuroscience, medicine, and use the ICT for understanding such function at different level. So the Human Brain Project is divided in 12 sub-projects. You have the first 4 sub-projects that are really neuroscience, from collecting data from mouse brain, collecting data from human, understanding cognitions at a different level, and the SP4 was in theoretical neuroscience. And you have also the platform to which you can access through the Human Brain Project portal, the Informatics that gather data from different scale, the brain simulation, which is try to model using computational modeling to simulate neuron and higher level of representation, high performance computing, and the medical informatics platform, neuromorphic computing, and neurorobotics. The challenge, as I say, about human brain, about the disease, you know it all, is that is that we don't know much about the brain, we don't know much about disease, and there's something interesting about the human brain when you look at it from the clinical perspective, is that the brain is very resilient. And then often when you see this symptom, when the symptom appears, is often that's damage that's very profound. For example, when you see in Parkinson's disease, which is the effect of certain basal ganglia regions, they're often affected at 70% when you start to see the first tremor, that's a visible sign. So this is why it makes it difficult, because we cannot, it's not as visible as a type of disease. It's like this box is completely closed. And then this is one of these challenges. And then the way that there's no objective measure or biomarkers for treatments. As you know, drug development is slow and is also expensive. And one of the reasons that we believe can accelerate the understanding of brain disease is a collection of data. So this is something that the medical informatics is doing, is collecting data not only from research but also from hospitals, from the patient themselves. And once you have collected the data, you really need to have this sort of integrative model that go through the different scale, and how you can find some sort of, through computational modeling, something that will explain the manifestation of disease or what you see at the brain level. Here I just listed the methods that you can do in human, fMRI, EEG, DTI. We can do tractography, we can do dynamic causal modeling or other type of modeling to really understand what's the interactions between the brain regions and what caused the disease. So I hope that during this week you will have the option to see this different way of modeling data and the way that they are affected through disease. I will say again a few words about the medical informatics platform. So the medical informatics platform, as I said, try to collect data, real patient data from hospitals. And the reason is that we have a discrepancy between patients that go to research study and the one that go to hospitals. So the patient that go to study, for example, if you want to study dementia, Alzheimer's disease, and you are a researcher, you will create a cohort and you have your exclusion criteria. You will say, okay, I don't want patients that have stroke, I don't want patients that have this, I want patients that have that. And you are creating sort of this artificial patient that really doesn't exist. When you look to patients that are affected by dementia or any type of disease, the first thing that you see is this comorbidities that they often have stroke before, they have history of psychiatry, etc., etc. And the question is that, is it deterministic or just the fact accumulation of age? So it's very important to have different type of data, different angle, and different view to try to build our models. In the medical informatics platform, we are collecting data from mainly 5 hospitals, and many more are coming. And as I said, the goal is really to build the tool to federate the data, and we have few issues about privacy. I will not go on about this. And work with the clinicians at hospitals. And our goal is really to develop the tool for extracting what we call the biological signature of disease. And the data that you find in hospital now, they are very interesting. There's 2 types of data basically that you find in hospital. There is data that are very few gigabytes, and this contain basically when you go to hospital, information about your insurance, your claim, your finance, the diagnostic, etc. And this is it's quite rich information, a lot of patients. Like you can have millions of records, but not interested that much in terms of biology. It's very narrow and give you just information about sociodemographic data. But as you know, more and more instruments are introduced to hospital. You can collect information from MRI scan, from EEG, from other type of instruments and sensors. And this now is growing, and you have terabytes of data that are not collecting every patient, so they're quite narrow in terms of number of patients, but quite deep in terms of information that we can collect. So what we try to build here is a sort of personal omic model, what's called panomic model, and we try to get this data and really try to harmonize in a way that's going different level, is to present the phenomenon, the physiome, is about anatomy, is about genes, etc. And this allows us to be able to compare this data from places to places. So once we collect this data from different hospitals, or we can really align. So one of the difficulties is that the data are not harmonized through different places, but looking at what we're measuring, we can realign this data. And what you have to think is that also is not a view of what is a patient. So a patient is a trajectory in this sort of space, and we have now a mean to create a multidimensional space that allow us to see similarity and differences between patients. So if you have priori hypothesis, you can do case control study, you can do predictive medicine if you want to predict which biological measure lead to a certain phenotype, or we can do what's called perspective medicine, which is basically stratification, and follow up these patients and see if the biology stratification certain patients in certain group lead to different treatments or different trajectory compared to the classical classification. So I will not go into detail about how it works, but we have developed certain system for privacy. This is the IT part, but you will see it in the platform. It puts certain constraints. So basically, in a nutshell, the data that is in the platform don't leave the hospital. So basically, the data are in different places, and we don't centralize this data. So we try to do the analysis in situ in different places, and we try to find mean to combine information. So why this is useful? I think this is useful already now. There's different clinicians working with us that come with interesting questions that they want to study. So for example, what are the factors that influence disease progression? And you will have a talk, I think, this week about this. This is very important to see which are the risk factor basically for certain type of disease. What are how we can differentiate between different type of pathology, for example, between vascular pathology and AD phenotype. Are they the same or not? So this is something that is very recurrent nowadays, the vascular pathology, how we can differentiate between different subgroups, between, for example, Alzheimer's disease and frontotemporal dementia. And basically, there's also all this unknown that there is in the population in a clinic, people that we cannot really classify, they don't really belong to, let's say, the textbook classification. And here, for example, using unsupervised method for machine learning or our knowledge, we can try to find what are the characteristics of these individuals that are different. There is some issue about already when you start collecting data, I mentioned before, how to harmonize it, how to make this data comparable from one center to the other. And we use approaches from so-called computational anatomy, basically, to extract information about the brain and to align between the different center. And we show that these measures are quite robust. And even if you have different type of scanner, different type of brand of scanner, head coils, etc., they're quite robust to give you an estimation of gray matter volume, cortical thickness, and other measures. We will see during the presentation how we can basically build the questions in the medical informatics platforms and how you can try to build different methods to answer this question. So the question ranged for, as I say, what are the risk factors for certain type of disease? You can go from genetics to brain imaging, or vice versa. Go to combining different type of data, and we'll have many challenges for you if you can also help us to find different way or methods that we can introduce in the platform. But we'll go back to this. This is some of the results that people have obtained already in the platform. As I said, finding this biological signature of disease. So basically, using unsupervised method to try to find a signature, which is through this representation, multi-scale representation. And we go to different cohorts to validate that this finding is replicable. Because when you do clustering or supervised methods, you always find cluster. The question is how you can validate that. And this is what we do. The method is, the platform is making use also of the available data from MRI scans. So we have methods for measuring brain morphology and summarize this in a way that it preserves privacy. So basically extracting the meaningful information from brain scans. And I have here slide a summary. I'll go through the handle session later. The disease signature, the disease progression. We also try to find this objective measure. So basically how we can use indexes, create indexes based on the biological data that correlate with the clinical diagnosis. So basically how we can convert this high-dimensional data to very few number that are meaningful for the clinicians. And we can also identify the early sign of AD. You have here one of the slide with the brain. So basically these people are in fact not even early AD. They are, let's say for the clinician, they're healthy. They're completely asymptomatic. These are people that have no symptoms at all of dementia. But despite that, using some of the approach that will be introduced to you, we can identify, in fact, that they have certain pattern of atrophy, which is similar to to Alzheimer's disease. One of the difficulty when you study brain disease is the confound of age. So basically, many of these diseases that I'm talking about, neurological disease, they happen at a later age. So basically, we need some sort of good reference model about what's happening through age, and then using also these different measures, we try to build trajectories about the age that we can use this as a reference. So we have created many of these tools that people can now, when they're clinicians, they can compare one individual patient to different cohorts. This is my last slide. Okay. So just to summarize, one of the important issues, and I repeat again, is really the standardization of clinical research and getting this data in these panomic models that will encompass measure about the brain, molecular, proteins, etc. This is very important. The extraction of brain feature from the multimodal imaging data, adjusting for the effects of age, and how we can validate new type of dementia subtypes, and how we can find evidence for building disease severity index that are biology based and not just symptom based. So the platform, in a way, try to create this link between scientists and clinicians through the use of data analysis and statistical models. And as you know, this is very important because this benefits the patient and the society at large. So I will finish here. I have a few more slides, but I think I will finish just here. Thank you very much. And if you have a few questions about the program, about the sorry.